Okay, we're talking about elastic potential energy this time. So as a reminder, the elastic force looks something like minus kx in the I hat direction. So we're going to think about our displacement as being something like dx, also in the I hat direction. So first, we'll find the work. That's the integral of our force dot product with our displacement from some initial to some final value. And if we run through this, we're going to get minus 1/2 kx squared evaluated in our limits. So minus 1/2 k x squared plus 1/2 k x naught squared. All right, the change in potential energy elastic is the negative of the work done, so it's going to be 1/2 kx squared minus 1/2 kx naught squared. And for that, it implies the elastic potential energy has a form that looks like 1/2 kx squared. Now you probably remember seeing that in your 2AG class if you've had the Mount Sachs sequence. If you've had the other sequence at Pasadena, you may not have encountered this before, but there you go. So it is interesting, you end up storing energy regardless of whether you're stretching or compressing, precisely because we're squaring the quantity, so the sign of x isn't going to matter. Let's see, anything else I can say about this? I don't think so. I can talk a bit about the picture that's going on. You start out, let's say your initial position is somewhere here where your 0 would be there. And then you stretch it even more to some final position. Then you could calculate the energy stored in that way. You technically could also deal with starting out compressed and ending up stretched, or starting out stretched and ending up compressed, or even what happens if you start compressed and end up at uncompressed at 0, or start at stretched and end up back at 0. And that's frequently how you will see this used in the problems that are coming up. It's a short one, but I'm going to call it there.